My name is Ravi Maduri. I'm a senior scientist at Oregon National Laboratory and a research faculty at the University of Chicago at the Human Genetics Department. Um, so I'm presenting some of the work that we've been doing in the context of federated learning. This work has been funded by um, U.S. Department of Energy and National Institutes of Health in the U.S. Um, I have a bit of a outline for what I want to cover today. Want to talk about motivation and why we wanted to create federated learning and describe and define what federated learning is all about and how it works, um, and talk about the importance of measuring data readiness for AI and why it's important um, and why it is important, especially in the context of federated learning. I'll then move on to describing the capabilities we've been working on in building the privacy preserving federated learning capabilities. I'll talk a bit about the design that went into building this capability and a couple slides on what we were able to accomplish using this federated learning. And I think one of the fundamental things that one of the fundamental drivers for this work is the the desire to build robust AI models that can withstand uh, shift in data distribution when these AI models are applied in real world situations. So, without further ado, I'll just go to the motivation of federated learning. Um, One of the important challenges we have in developing and applying AI to real world situations is that, um, fundamentally, artificial intelligence is a data and a compute hungry sport. The more data you feed in training the AI models, the better the model is in responding to and understanding and providing quality feedback and aid. And one of the important challenges in finding data for training AI models is that we are gradually running out of publicly available data that we need for training these AI models. As you can see in the chart here, in the first chart, the amount of data that is available publicly and kind of projects at some point in 2028, the AI companies that are training these models will run out of publicly available data. And in that context, how do we further improve the accuracy and robustness of these AI models? Two things come to mind. One is using private data. The other option is to use generative AI methodologies where you can generate data from existing data using AI models again. One of the challenges with the second approach is that um, it doesn't really capture the changes in the data distribution. Models don't know what they don't know. So the problem would be that um, the synthetic data or generated data will amplify the bias that these models already have because the generative AI methods are not going to generate data in a distribution that they are not previously trained on. So this kind of lets us into a slippery slope of models where the bias is gradually increasing and models that are sort of not very uniformly applicable to different parts of the world or in different use cases. In the first challenge, where using private data or unlocking private data to be a source for um, data for training data for these AI models, the challenge is that some of this data can be private and sensitive in nature, especially if you talk about if you're looking at developing AI models for biomedical applications. A lot of this data, especially patient level data, is private and considered sensitive. And it comes in different modalities. As you know, in biomedicine, we have electronic health record data that captures the phenotypic information about a patient. And then we also have multi-omic data, genomics, proteomics, and a lot of imaging data, X-rays and MRI. So unlike the foundational models like ChatGPT and Claude that are trained on text and videos and images. Um, these are different modalities. These are quite distinct from the modalities that the current foundational models are being trained on, and they also come in different distributions. As you know, a patient health record spans the duration of life of a patient, while a kind of a genomics data remains constant during a person's lifetime. So they kind of have different distributions and have different challenges in terms of measuring why this data could be important for this model. And um, in domains that often house private data, there are many policy constraints and regulations that need to be taken into account. For example, in certain domains, intellectual property is an important aspect of the data. So you would want to make sure that the intellectual property of the data is retained when you train an AI model on that particular data. And in some domains, especially in domains that often generate data that is of national importance, you have national security constraints um, and data sovereignty needs to be respected and maintained. For example, some of the data from countries like North South Korea and India cannot move the sovereign boundary of that country. Um, so in some areas, you have policy requirements like data usage agreements. For example, I know some of you are familiar with H3 Africa. In order for somebody outside Africa to get access to data being generated in H3 Africa project, you would need a data usage agreement. And same is true with the consortiums like UK Biobank and large scale biobanks like all of us and other places. So all of this, the non-technical policy challenges of the data availability, especially in the context of private and sensitive data, leads to kind of a data scarcity that leads to models that are often underspecified and are less robust in when they're applied to real world situations. So um, this is often called as a data wall. The data wall is basically a kind of a situation where publicly available data is all being used for training, and you're kind of looking at some private data to improve the performance of these AI models. So this is a very a well-known phenomenon for a lot of companies that are building frontier AI models. And one of the other interesting thing is that um, the the current paradigm of building frontier AI models is basically um, trying to get all of the data that is available in the world in one location and perform a lot of computing on this data, use a lot of computing on to train AI models, and then use these AI models. What that creates is this um, kind of a challenge where the amount of computing that is required to train AI models is also increasing by every year, and we're kind of getting to a point where um, moving all of the data to a central location not only violates the data privacy and security constraints, but also may become practically impossible. Not only because we don't really know how good the data is, and the amount of data that needs to move is also substantially more than what we can practically store in one central location. So these are some of the real world challenges that a lot of research organizations and frontier AI companies are facing in building next generation of models that are more robust and applicable to real world challenges. And to kind of move this further motivate this problem, so this is again, when we started looking into this, we realized that this is not a new problem. This has been a challenge ever since statistics were being used to help make decisions. And statisticians often call this phenomenon as shift in data set, and how it affects machine learning and AI models. And one of the important um, uh, paper that motivated our work in this area is this particular AI model that is embedded in a hospital electronic health record system that essentially looks at a patient and makes a determination whether the patient is at risk of developing sepsis infection while being at ICU or in an emergency care situation in a hospital. And this model is an AI model and has been trained on data set that has been kind of not a more recent data set, but has been trained on data that is quite old, and outdated. At the when COVID pandemic struck, a lot of these models, because they haven't been updated with the symptomatology of COVID, have started generating a lot of false positives. Basically, saying that a patient is generating or is at risk for sepsis because they got confused by that the COVID symptoms are very similar to symptoms of sepsis. And it often led to physicians to kind of turn off the alert that that system is generating for a particular patient because it was considered false positive. But it also made some of the real alerts be ignored by physicians and led to some serious conditions for some patients that were really were infected by were at risk for infect of sepsis. And as some of you know, sepsis is a very dangerous condition and often leads to death of the patient if it's not treated within 24 hours. So this is a very important lesson that basically tells us that the models that are being used for determination of patient mortality need to be updated very frequently so that they are reflective of the latest changes in advent of pandemics like COVID and other pandemics. So this the work that has been done in this context was published in New England Journal of Medicine, which is one of the most important high impact journals, and it's called the Clinician and the Data Set Shift in AI. And this paper kind of served as an inspiration for us to uh, really think about what is the core challenge here and how can we build a system that will help us avoid this particular, or that would help us solve this particular challenge and help make models more robust in nature. So we after some uh, prototyping and some thinking in our group at Oregon, we thought federated learning as a form of distributed learning would really help solve this particular challenge. And federated learning is essentially a kind of a collaborative learning process where there is no central data storage, or you're basically training an AI model without sharing data sets across multiple organizations. Um, and one of the fundamental advantages of federated learning is that data stays local. It doesn't move. The model updates or every site that is participating in a federated learning experiment does local training on their own data, and they share these model updates with a central server, and the server aggregates the model gradients that are being received from individual sites, and at every round the central server aggregates the model and sends a new set of gradients to the local site. So um, one of the important things in federated learning is that it reverses the paradigm of how AI models are trained. Typically, models are trained by storing all the data in a central location, and then using that centrally located data to train AI models. In this federated learning paradigm, you're sending model to where data is instead of sending data to where models are being trained. So it kind of is an important distributed learning paradigm that changes how things are done in federated learning. And one of the, as I mentioned, some of the main benefits of federated learning are the fact that the raw data never leaves local sites, makes it very important, makes it very applicable to situations where data privacy and data locality are important. So federated learning kind of solves the challenge of data use and privacy that is involved in data sharing. Um, it is also efficient because it prevents a lot of data to be moved to a central location. So by moving the smaller model gradients, you're basically preventing large data sets to be transferred and stored in a central location. Um, because of the distributed nature of the paradigm itself, it is inherently scalable. And these are the same concepts that are used in building the World Wide Web or the internet that as we see it. Internet is made possible because you have protocols that are designed to allow for distributed discovery and distributed processing. One of the most widely used federated learning algorithm is called federated average. And basically what federated average does is it averages or it aggregates all the gradients that are received from local sites and creates a new set of gradients. It doesn't really do anything complex, does a mathematical average and then sends a revised set of gradients. Um, we have been developing the framework that enables federated learning for a few years now, and it's openly available. And one of the important things we made available as part of this framework is to enable training using a cryptographic concept called differential privacy. And I'll talk a little bit about that in a later on the later stage. And the the framework itself allows you to train AI models across multiple different computational resources, from high performance computing resources to cloud to edge devices. So the federated learning itself isn't without a lot of challenges. One of the common criticism for federated learning is that it leads to models that are probably less accurate or less efficient when compared to centralized training, because the models don't really have access to all of the data from all of the sites, and that's a valid criticism. But the fundamentally, uh, even though the model might be less accurate when compared to a model that is centrally trained, it also leads to more robustness of the model itself. In the fact that the model actually, when it is training, learns distributional changes or differences across data distribution across different sites, and hence results in a model that is more robust of shift in distribution. Um, so there's also a kind of an issue when you have sites that have data that has a lot of heterogeneity. So uh, this requires a kind of a careful tuning of the model, and this is something that we focus on in our capability to really use some of the tools that we developed called for measuring AI data readiness to really understand the heterogeneity in data and figure out a strategy that will allow us to kind of work around the heterogeneity. Um, so as I mentioned, some of the techniques we use for preserving privacy in federated learning is using differential privacy, and differential privacy also um, results in a kind of a loss of accuracy because of the noise that gets injected into the training data. And we kind of try to address this by really understanding what amount of noise is really required to ensure data privacy, and not kind of use the same differential privacy budget for all kinds of data modalities. Um, so the final challenge in using federated learning is the overhead that is introduced by communication. So for every round in federated learning, um, uh, when a training round is complete, the sites that are involved in federated learning sends the model updates to the central server, and the server aggregates the gradients and then sends back an aggregated weights to each client, and that kind of creates a lot of communication that goes on between the sites participating in the federation and the server. But we so that can create a bit of an overhead, and we address that overhead by leveraging techniques called parameter efficient fine tuning. Basically, these are some of the algorithmic improvements that would make the communication much more efficient, and as one of the main research topics for our group is to uh, minimize the impact of these challenges on the overall model performance and accuracy. And we published quite a few papers on developing new strategies, new algorithms, new hyperparameter fine-tuning strategies that would allow us to overcome some of these challenges, and make federated learning a viable strategy for building frontier AI models for science. So some of the challenges I talked about, like that, understanding the data heterogeneity, understanding the non IIDness of the data is important. So we built a capability that would allow us to measure the readiness of the data before model training is started. We built a capability called AI Data Readiness Inspector. Basically, it's a set of Python tools that run at each individual site, and runs analytics on the data, on the training data, and allows a not only the central model trainer, but also the individual site owner or the data owner to really have a good understanding of the data that is being used for training. So this is basically something that you can download and install and use it independent of our federated learning framework, just to sort of get a good understanding of how good and how what is the quality of the training data that is available before you start model training. And it measures there are many dimensions to how we measure data readiness. First, we measure the quality of the data, and as some of these definitions uh, uh, are common across all of the data modalities. Like, for example, some of the case control distribution, or some of these measurements are very common, like fairness, for example, making data findable, accessible, interoperable, and reusable. These are all agnostic of the data modality itself and are universally required for high quality data. So we encapsulate all of that in a base Python framework that could be used to measure these foundational qualities of data, to give a idea about how to give an idea of the quality of the data before you start training process. So the key metrics that Adrian uses to evaluate are completeness of data before the training, accuracy in terms of if there's any uncertainty, quantification in terms of data quality. It tries to capture that. It also looks at there's any duplicated data. Sometimes it happens that we have the same kind of data repeated in multiple places. It also captures importance of different features as they apply to model training. It measures fairness of the data. It measures privacy of the data. If there's some of the private data that is being leaked into the training data, this inspector catches that before you start training. And finally, it measures how compliant the data set is to the fairness principles, or the fair metrics. It's very extensible. One of the reasons why um, we made it very extensible is that some of the data readiness metrics are very subjective to the data that is being used. They're very each data modality might have a different kind of a metric for measuring data readiness itself. So we made it very extensible so that you can add custom capabilities to measure data readiness metrics for data modality that is being used for building this particular AI model. And we published quite a few papers on this in various conferences, and I put one citation there that gives an overall idea about the inspector itself. So um, what Adrian does is it provides a not only a report but also a visual representation that allows you to look at the quality of the data itself. And some of these metrics are completeness. You can look at different graphs and different visual representation of the training data to really measure the readiness of data before the model training happens. So next, I'm going to talk a bit about how what are some of the capabilities of the federated learning framework that I talked about before. As I mentioned before, it is a distributed learning capability implemented in a way that each site um, trains a model on its own data and shares the model gradients to a central server that aggregates that gradients, and then the training process proceeds by each epoch, where the server originally so the training process starts with the federated learning server, and the server has a AI model that the creator of the federation has decided to use. And the model architecture gets sent to the sites participating in the federated learning experiment. And each site uses the model architecture, trains the model on its local data, and generates model gradients. For each training round, all the sites participating in the federation sends the model gradients to the server, The server receives all the gradients from local training from different sites participating in the federation, uses a algorithm like Fed average, or we created a bunch of new algorithms that do much more effectively calculate this gradients, generates a kind of a resulting set of gradients, and then sends the set of new gradients to all of the sites participating in the federation, and the training continues for every round. The server aggregates the gradients, sends it back to the sites, and the cycle continues until the model converges, and you actually notice that the model performance is increasing for each round. And this is a kind of the framework that we built. Um, it's a very modular in design. Basically, there are three major components in federated learning from a technology perspective. There's a server itself. The server is the one that is orchestrating training at individual sites, and it has a aggregation strategy, a privacy strategy, and being able to schedule the local training across multiple participants of the federation. There's a communicator. The communicator is basically how the server and the clients are communicating, and that involves a bunch of other technical capabilities that kind of use authentication so that the clients are authenticating to the server in a secure manner, and each client has a task controller that dictates how the local training happens, and whether the local training is using an HPC to perform the training, connecting data connectors that connect the training data with the model training itself, and the compressor, which is something um, that allows you to compress the model gradients so that you can effectively communicate the gradients to the central server. The communicator, the third module is the client agent itself, that one that sits on the client, and it is the piece of software that interacts with the local data, interacts with the local HPC, and then communicates the gradients through the communicator to the server agent. So it's a pretty kind of a simple technical architecture. Three components, each doing a very well-defined task to enable federated learning. And we implemented several communication strategies to suit for different use cases. We support MPI communicator, and the most general purpose communicator is gRPC, which is basically a web-based communicator. We also support Globus that allows for more high performance communication strategy across distributed computing resources. Um, in the US, we have a capability called Fabric, which is a software defined network that allows for more robust network communication across different participants in a federated learning experiment. So, as I mentioned before, we developed quite a few algorithms to improve the overall effectiveness of federated learning. We created new training algorithms. We created new privacy preserving schemes. We support differential privacy and homomorphic encryption of the training of the model gradients. Different communication protocols, gRPC, MPI, and Globus communication. We also basically we created this on top of a popular AI framework called PyTorch, and so that people who are familiar with PyTorch already can use this very easily. So some of the additional challenges after we created this framework that we realized is that uh, because of heterogeneity that is involved in computing resources with different schedulers that are being used in different HPCs, it often leads to a lot of work in terms of setting up a federated learning experiment across multiple sites. One of the important things that we wanted to do with this effort, and this is the work that Matthew in my group is leading is to create a worldwide federated learning network that trains AI models across data from different parts of the world. And because of um, uh, the differences in how individual HPC and individual universities are set up, there's a lot of work that is involved in setting up the client agent and have it integrated with the federated learning network. So one of the things that we built for accomplishing to make it easy is we created a lot of documentation. And Matthew, I know, is working with you all to set up a federated learning node in Nigeria, so that you are part of the world, an international federated learning test bed that includes other countries in the world, including Japan, India, Germany, and a few other countries that are participating in this network. So when we set up this federated learning network, we can do use cases like the following, right? So one of the things we did was we created a federated learning network to improve to create an AI model that would be more accurate in predicting COVID from chest X-rays. And this is the work we did with the University of Chicago and other universities, where we created an AI model that has a better performance than traditional models in predicting onset of COVID for using chest X-ray. And in one of the in the bottom of the slide, we demonstrate how using differential privacy will enable will basically make it impossible for a attacker to recreate training data from chest X-ray. So the stronger the privacy, the harder it becomes to regenerate training data from the gradients. So this is an older slide. As I mentioned before, this framework is open source, we have quite a few people using this. It's available from GitHub. We have two sets of users. We have developers who use this to create new algorithms and validate, test it. We have users who use it in multiple domains, including biomedical domain, electricity, smart grid challenges, material science. A lot of different domains use this capability to do discovery. And it's very comprehensive. It addresses many heterogeneity and privacy challenges. It's easy to use. We have a lot of documentation, a lot of help in making it really easy for users to use it and set it up. Very extensible, so you can add new algorithms, new capabilities, new easily. One of the reasons why we want to build this, and this is the work that Matthew is currently leading, is to build a system that learns in a continuous manner. So basically, if you have a worldwide federated learning test bed where you can uh, quickly validate how good a particular model is by having the model be trained and used in different locations in the world, and continuously improve the model by training it on local data, so the model is aware of some of the distributional shift that happens when the training data uh, when the data that is used in training is developed in a different location than where the model is originally built up at. So that's all I had. Hope this was useful. Happy to take any questions at this point.
Wow, thank you so much, Dr. Ravi. That was great. Thank you so much. Okay, so the floor is open. If you have question, please you can just raise up your hand or you type it in the chat box. I personally have questions, but let me allow people. Okay, so I can see hands up already, Mr. Uche. Okay, Mr. Uche, please unmute yourself and ask your question. So we have like 10 to 15 minutes for questions. Dr. Ravi, you're okay with that, right?
Yeah, that's fine. Yeah.
All right, thank you. All right, so Mr. Uche, you can unmute yourself and ask your question, please.
Please confirm you can hear me.
Perfectly.
Okay, good. Thank you, Dr. Ravi, for that presentation. I just wanted to find out, is it possible to completely eliminate data leakage between sites in federated learning? And if the answer is yes, what is the best strategy to achieving this?
Eliminate what? Sorry, say it again.
Data leakage between
Data
sites.
leakage. Okay. Um, yeah, so that's a very good question. I think using differential privacy will two things. One is using the AI data readiness inspector. You can really try to see if there's any duplicates in data across different sites. And then using differential privacy, you can secure the model gradient so that you can prevent anybody from regenerating or recreating the training data the from the from the from the training data from different sites. So um, the the data leakage itself is a it's a more of a local problem. Like for example, if if you're splitting your training data into test train validation and you have leakage, like you have the same data that you're using to train that is used to validation, then that's not a good situation, right? So there are two parts to the question. One is you have to prevent data leakage in a local setup. That is something that each site has to do on their own. And then using AI data readiness inspector, we kind of prevent overfitting of the model itself. If two sites have similar data sets, then we can remove it from the federated learning experiment itself. Hope that answered the question.
Mr. Okay.
Yes.
All
Yeah,
right.
yeah, that's fine.
Thank you. All right. So, Mr. John Akintayo, please unmute yourself and ask your question.
Thank you very much, Professor Ravi Maduri. So my question is related to the data leakage. So I'm much concerned about when the weights are being sent back to the server for aggregation. So I'm thinking that in the course of sending the weights and bias back to the aggregator, is it possible that some of the data is sent? That is one. The second question is that is it possible to inject codes to copy the data without the information of the client server? So those are my two questions, sir. Thank you.
Yeah. So one of the important things that we do in APPFL is to implement mutual authentication and authorization. So the server and clients are authorizing each other to talk to each other, and that's implemented using a kind of a secure channel that is secure using TLS or transport level security. So it's often very impossible to essentially do something that 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 results in data stealing. And so that prevents a attack like a man in the middle attack or somebody intercepting the model gradients that are being sent from server to the client and using that to reconstruct training data. So that is one measure. The second thing is again differential privacy, which is something that gets added to the training gradients, so that somebody who is either the client or the server, it makes it impossible for them to recreate training data because of the noise that was added to the training process. So makes sense.
Thank you very much, sir.
All right. Thank you so much, Dr. Ravi. We have a question in the chat box, I think from Mr. David. He said, did you make use of the FedPro's algorithm?
No, no, I read about it. I think that's one of our colleagues in our team has used it. I personally haven't used it. So I think Zillingan in our team has written a paper comparing different algorithms and their effectiveness in using in federated learning, and FedProx is one of them.
Oh, okay. All right, thank you. Professor Adetibasa.
Okay, thanks, Ravi, for that very explicit presentation. Okay, my first question is on the high drain. That's the AI data readiness inspector. I'm wondering, can this tool be used for AI use cases or workload that are not federated based, non-federated learning based workload? Can that AI
Yes.
inspector be used for that?
Yes.
Okay, okay, good. The second question, you mentioned that one of the major problems with the APPFL is lack of uniform authentication and authorization to enable secure training of models. And I was looking at, you have Google Cloud, maybe as a client, maybe you have our FedGen platform as another client, and you have another client at Argon Lab, for instance. This authentication and authorization, how do we achieve uniformity?
Yeah. So one of the again, there is no magic bullet. So one of the ways we achieve um, like better integration with identity and access management is by using Globus, which is a University of Chicago project that kind of implements a single sign-on or uniform identity and access management. So this is something that Matthew has been working with your team to set up a Globus endpoint and uh, have Covenant be part of the Globus system of identity providers. And by using this, we create a very secure federated learning experiment while with Argonne and Covenant and other places participating in the experiment using their institutional credentials. So this is how we are kind of implementing this.
Oh, beautiful. I think the Globus idea is a good one. Okay, so my last question, the slum in the architecture for using APPFL, a slum actually handles workload management during training. Does it stay on the server, or it has to be on each of the clients that is participating in the federated learning?
Um, can you ask the question again? Sorry, I didn't. Yeah.
Slum node, that's for workload
Oh,
management.
The Slurm node. Okay.
So does
Yes,
this
the Slurm node.
to be on the independent clients in the federation?
Yeah, yeah. I think that training can happen both on the node where you have APPFL client running, or it can be submitted as a job to a Slurm HPC cluster. So both of those options are supported.
Okay, great. Thank you. Those are my questions. Thank you, Ravi.
Okay, thank you so much, Prof. I was supposed to ask my question before Prof. So, but yeah, I think I will also ask a question as regards the AI dream that you talked about. That's the AI Data Readiness Inspector. So I found that very, very interesting. Then I was wondering, how does the inspector measure the privacy and the fair principle compliance? How does it do that? What algorithm?
Yeah,
That's major.
yeah, yeah. So the fairness compliance is measured using So there was a toolkit that was developed by NIH on it's basically a Python-based tool that has a criteria for measuring whether the data is findable, accessible,
Okay.
interoperable, and reusable. It uses that tool to generate a score for a particular data to measure the fairness part of it. For the privacy, there are many tools developed by different organizations. In the US, there's an organization called NIST or NIST that developed some capabilities on measuring the privacy requirements of a particular data. So we've been using those capabilities to generate these reports for Adrian.
Oh, okay. Thank you. Then I think my last question, I think you mentioned it, the privacy algorithm that the APPFL uses, that's your framework. Then I was wondering, is there an hybrid approach? Like, did you try to combine the differential privacy with the homomorphic encryption, or you have or is custom? Did you develop your own custom privacy algorithm? Is there a name to it? I just want
Yeah.
to. Okay.
Yeah, we used so we started with something that was already developed called IADMM, and that was a very good algorithm, and we implemented that algorithm and used it. But then I had a postdoc who developed a much faster version of that, and we use that going forward. So I think the idea of differential privacy is very well known, and there are a lot of algorithms that have different strengths and weaknesses in implementing differential privacy. So we leverage a lot of the openly available algorithms to implement this differential privacy in our framework. So and if you have a algorithm that you want to use, we can. I mean, that's something that APPFL allows you to. You can integrate that algorithm as well very easily.
Oh, okay. That's awesome. Thank you so much.
I really want to kind of emphasize one thing before I leave is that I think this is a good opportunity to for us all to work together, and any help you can provide to Matthew to complete the setup of federated learning in your at different places in the university, like Covenant or Lagos or other places. I think that would make this impact very big. So thank you for your help on that. With that, I would say bye and thank you all for
Okay.
listening.
Thank you, Ravi.
So
So
much.
we'll come back to you on how we get to this stage of by putting the APPFL on our notes at
Yeah.
Covenant and at LASU. So, and how we ensure that this translates to tangible impacts for the
Thank you.
participating. So thank you very much.
Thank you. Bye.
Thank you very much, Ravi.
All right, Dr. Ravi, thank you.